In an online game, tens of thousands of players are spread across different score tiers. You watch your rank, how many players score no higher than you, which is essentially a prefix-sum problem. And players keep gaining points, so the distribution keeps changing. A Fenwick tree keeps both query and update fast. Split scores into 8 tiers. Each tier records how many players have exactly that score. Here we show the raw counts, not Fenwick tree values. To count players scoring less than or equal to 7, the direct way is to add up the first 7 tiers one by one. The more tiers, the slower. ON in the worst case. A Fenwick tree represents this tree with just an array. Each node is labeled index, value, where the value is the sum of players over the range it is responsible for. The key is lowbit, the lowest set bit of the index. Node I covers I minus lowbit, I plus 1. I, lowbit 3 equals 1, covers 3. Lowbit 4 equals 4, covers tiers 1 through 4. So, node 8 covers all 8 tiers and stores the total of 14 players. A handful of nodes can assemble any prefix. Now use the Fenwick tree to answer the same question. Count players scoring less than or equal to 7. This cumulative count can help compute a rank, but is not itself a rank under every ranking convention. Start at index 7. Take the current node's value, then subtract its lowbit to jump. 7 minus 1, 6, 6 minus 2, 4, 4 minus 4, 0, stop. Add those 3 nodes. 4 plus 3 plus 6 equals 13. So 13 players score at most 7. The whole query touched only 3 nodes. O log n. A player moves from score 2 to score 3, so the raw array changes in 2 places. A 2 decreases by 1, and a 3 increases by 1. The Fenwick tree performs 2-point delta updates. First, apply the decrease at score 2. Walk upward with I plus equals lowbit and propagate -1 to nodes 2, 4, and 8, changing them to 2, 5, and 13. Then apply the increase at score 3. Node 3 becomes 4, node 4 returns from 5 to 6, and node 8 returns from 13 to 14. Each point update is O log n, so the combined work is still O log n. The Fenwick tree cleverly partitions the array by lowbit, making prefix-sum queries and point updates both O log n. It uses less memory and far less code than a segment tree. Any range sum can also be computed as prefix r minus prefix l minus 1. It fits additive, invertible counts and sums. Range updates and aggregates, like minima, usually need other structures or extensions.